Okay, so we're going to today look at graphs of, as it says, sinusoidal functions is how you pronounce that. A sinusoidal function is a function that's written in terms of either sine or cosine. Okay, we're going to find out why it actually doesn't matter if it's sine or cosine. These are also sometimes called trigonometric functions, but trigonometric functions would include sine, cosine, as well as the other four graphs. We're not going to look at the other four graphs in this course. They're not as useful. They don't model real-life behavior as often, and you'll see them next year in grade 12. So we'll just look at graphs of sine and cosine. And you started that yesterday, looking at what y equals sine x looks like and what y equals cosine of x looks like. So what we're going to do today is we're going to take those base graphs that you came up with, and we're going to apply transformations to them. Just like we did at the beginning of the year, just like we did with exponential functions, but with sine and cosine. So a couple things you need to understand with all this lesson. One is you need to know what sine and cosine look like. The second thing you're going to need to know is have a basic idea of how transformations work. Now, if you don't remember transformations too well, you'll actually get a pretty good review of it today as we go. In fact, sine and cosine are a great way of understanding transformations because they just, the curves transform very nicely, okay? A horizontal compression looks very different than a vertical stretch and all that kind of stuff. But actually, a lot of people who had trouble with transformations, it kind of all comes together when we start looking at sine and cosine. So to start with, if I just throw it in Desmos here, that's the graph of y equals sine x, done from 0 to 360, okay? Notice we talked yesterday about periodic functions, and this graph is periodic. Okay, notice that these are not V-shaped, they are smooth curves, okay? Notice that it's also the graph of sine x. We're also just graphing the height on the unit circle, or the y value of the unit circle, because that's what sine represents. Okay, so it's not a shock that we have 0, 0. 91, the sine of 90 is 1. The sine of 180 is 0. The sine of 270 is -1, and the sine of 360 is back to 0. And then we continue that pattern. Now you graphed a bunch in between as well. For example, the sine of 30 is a half, somewhere in here. The sine of 45 is 1 over root 2, somewhere in here. Okay, so that's what sine x looks like. Of course, it keeps going forever. It's periodic. What is this period? 360 degrees. It just repeats every 360, which makes sense. Think of Freddy the Frog, right? It repeats its height every 360. Where's the midline or the equation of the axis? Y equals 0, straight through the middle. How about the amplitude? What is the amplitude of the sine curve? That's what I'm saying. It's 1, okay? That's about it. Cosine, and the domain is XER, by the way, all the X values. You take a sine of any number you want. Cosine's very similar, but instead of starting at 0, 0, notice cosine starts at 1, 0, since the cosine of 0 is equal to 1. Okay? Since it starts at its maximum, it has to go down. The cosine of 90 is 0. Cosine of 180 is -1. Cosine of 270 is 0, and then back to the cosine of 360, which is 1. Cosine is also the x value of the unit circle. Freddy the Frog's horizontal distance from the center of the wheel. Okay, so another way of thinking about it. Notice you now also have, if you understand sine and cosine, and someone asks you, for example, what is the cosine of 180? If you sketch this graph, then the answer is right there. Cosine of 180 is 1. It's not the graph. You need to know what those graphs look like anyways. It's not a bad way of answering that problem. Okay, so back to our little handout here. We should be able to sketch sine and cosine. Now notice when I look, actually I'll go back for 1 minute here. Notice when I look at sine, there are actually 5, we call them key points. Right here, right here, right here, right here, and right here. Those 5 key points separate the graph into 1, 2, 3, 4 different sections. Okay? And they do a pretty good job of describing the graph. So when I go to sketch sine, I'm just going to do that. Okay? I'm going to start with my x and y. Okay, this is 0, this is 1, this is -1. Sine always starts at its axis, and then it goes up. Think about doing a frowny face, and then a smiley face, and it continues like that. And then we have these key points right here. Okay, this one is at 90 degrees, this is at 180, this is at 360, and this is at 270. Notice the key points are every 90 degrees apart. The period's 360. The 5 key points break the graph into 4 sections. Sure enough, 360 divided by 4 is 90. So they're 90 apart from each other. Think you could sketch that curve if I asked you to? 100%. Awesome. That's what I'm here. Cosine is similar to sine. It actually has the exact same shape. Okay? Just has a different starting point. Cosine starts at 1, which is its maximum. If you start at your maximum, you go down. I find cosine a little bit harder to sketch, but this helps me. Half a frowny face, smiley face, other half of the frowny face. All of that takes 360 degrees to happen. Well, this must be 180 then. Halfway between 180 and 360 would be 270. Halfway between 180 and 0 is 90. So there's the cosine. And of course, these do keep going. I mean, they keep going in both directions, in the negative direction and the positive direction. But there's one cycle of the graph, okay? Graphed over one period, which we call one cycle. And notice in each case, there are 5 key points. So now the idea is we can graph any sinusoidal function we want if they're in our special form that we already talked about at the beginning of the year, okay? Using what's actually called, people actually call it the 5-point method of graphing. All right, so sine or cosine could be our base graph, and we have A, K, D, and C. Do you remember what the A value does to a function? In words. Vertically stretch, absolutely. A is a vertical stretch. It might also be a reflection in the x-axis if it's negative, flips upside down. Very good. How about K? Yes. Horizontal stretch compression. What do you have to remember when you're dealing with K? The opposite of what you would expect to see, okay? The opposite. So if it's a 2, you're going to divide by 2, and so on, okay? It also could be a reflection of the y-axis, but I think you'll find with these functions, we don't often have to worry about that, okay? They're periodic. Reflecting the y-axis can be a little bit strange. Let's move on to this one. It's the next easiest one. What's that do? Up or down, absolutely. Vertical translation or shift up or down. And then finally, how about this guy here? Yeah. Horizontal shift. Remember, do the opposite of what you see. I mean, here it's just D because it's a negative D, but yeah, there you go. And then we talked about mapping notation. If you took the original functions, x and y values, which is now going to be either sine or cosine, one of those 2 functions, all your x values will be divided by k and add d, and all your y values will be multiplied by a, and then you'll add c. This is the simple way of graphing sinusoidal functions, is just apply that mapping notation to all the key points. I'll show you some shortcuts later on, but for now, that's probably an easy way to do it. So if I look at y equals -4 cos x plus 1, a nice, fairly easy one to get started. So our base function is obviously going to be cosine. And I can look at the key points on cosine. I've got the graph right in front of me here, so I can just list those points. 0, 1. The next one's 90, 0. 180, -1. 270 back to 0. 360 back to 1. And notice these graphs always kind of do the same thing. Cosine starts at its maximum, goes down to its midline, goes to its minimum, back to the midline, back to the maximum. Sine starts at the midline, goes up to the maximum, back down to the midline, down to the minimum, back to the midline again. We transform these points, we'll find that our new key points do the same thing. They either represent a maximum, a minimum, or a midline. Okay? Let's come up with that mapping notation. Every point here is going to become what on the new graph? I'll give you a minute just to think about writing that down. Got those points and you've got the mapping notation, you've essentially got it. Notice the x values, they're not actually going to change at all. It's just the y value. We're going to multiply them by -4, and then we're going to add 1. Okay? So this will be still 0. This is a nice easy one to start with. -4 plus 1 is -3. Okay, 90 is still 90. -4 plus, okay, just 1. 180. And the -1 becomes -4 plus 1 is -3 again. That doesn't seem right. It's 5. Thank you. The other nice thing about this is you can tell if you made a mistake. Because I'm like, there's no way it's -3 again. We're not going back to -3 that quick. 270 and 1. And 360 and -3. Yep.
It's the very first point, the very last point.
Yeah, why are they going to be the same? It's periodic, and that's a period. The period is still 360. Okay? So we'll find, yes, they will always be the same. Okay? Even if the period isn't 360, we'll find that we get them the same as well. Okay, we'll see that in the next example. For now, we'll finish off by sketching this. Okay, all right, so as you do this, it's a good idea to think about it. Notice that my midline is no longer at 0. It's actually at what? 1. Okay, 1's the middle value. 5 is the max, and -3 is the min. Okay? In fact, it's not a shock that the midline's at 1. You can look at the equation and tell it's going to be at 1. Because when you shift the graph up 1, that's the only thing that changes the axis or the midline. Okay? So as I draw this, I'm going to do this. That'll be 0. If my midline's at 1, I'll put that, like, say, right here. I've got a value at -3, so I guess my graph needs to go down to -3 now. I can put that about right here. And my maximum is 5, which I'll put up here. This graph starts at its minimum, and then it goes up. So it's going to do something like this right here. Okay, my sketch is not perfect, but there we go. That whole thing takes 360 degrees to happen, because this last point is 360, -3. I also had 91, so this is at 90. I had 180 and 5, so this is at 180. And I had 270 and 1, so this is at 270. You might appreciate the fact that I barely even glanced at those points to figure that out. Do you see what I mean? Like, I could just graph these points, which is basically what I did. But once I kind of realized that this was 360 and -3, do you get that this has to be 180 because it's halfway? And this has to be 90 because it's halfway? So the graph actually comes together very nicely. Okay? There it is. It's a, why does it start at its minimum? What is it about this that made it start at its minimum? Yeah. Yes, and reflected in the x-axis or inverted. Cosine usually starts at maximum, now starts at its minimum. All right, let's try this one. This one's a little bit trickier. We're dealing with sine now. Okay, so our base function in this graph would be y equals sine x. Using the graph at the top, sine x has 0, 0 as a point. 91, 180 back to 0. 270 down to -1, and then of course 360 is back at 0. Those are 5 key points. See if you can come up with the mapping notation for those points, or for any point. Give me just a minute to do that. Anybody want to take a stab at the x part? Yeah. Okay, so in general, that'll be x over 36. If you don't mind me writing that. Okay, go ahead. Add 2, though. Okay, it's the opposite, so we're actually going to add 2. All right? And then for our y's are a little easier. Yep. 10y plus 10. That's it. And we can do that to each of those points. Yeah, of course, 0 divided by 36 is still 0, but then we add 2, we get 2 here. And then we get 10. 91. Okay, does 90 divide by 36 nicely? You get, yep, 2.5. And then, let's see, 10 plus 10 is 20. Oh, 4.5, because I forgot to add 2, thank you. And is 20 right? I believe so, yeah. Okay, 180 divided by 36 must give you 5, I believe. And then you add 2 to get 7. And I get 10 again. Okay, notice the 7 here as we go on. Do you see that I can tell it's going to be 7 without even doing the work? Because you went from 2 to 4.5, now you're going to go from 4.5 to 7. You're just adding 2.5 each time. Since these points are evenly spaced out, the same will be true when I apply the transformations. The linear transformations we're doing, they affect all the points the same way. They don't squeeze some points closer together and some points further apart. They do the same thing to all of them. All of this graph has been horizontally compressed by a factor of 36. Okay? The next point, 270 divided by 36 plus 2, I guarantee you that's 9.5. Hey, you don't believe me? You can try and count that. And then I get negative 10 plus 10 is 0. And then 360 divided by 36 would be 10 plus 2, which gives me 12. I could tell without doing that that's going to be that. And then 0, I get 10. Can you tell by looking what our period is here? Good guess. Quite. Yes, we finished at 12, but what do we start at? 2, so it's 10. The period's 10. In fact, think about it. You took a period of 360 degrees, you took a graph that has a period of 360 degrees, and you divide all the x-i's by 36. So your period is just going to be 360 divided by 36, which is 10. Because this graph has a period of 10. And the 5 key points divide the graph into 4 sections. Sure enough, 10 divided by 4 is 2.5, and all those points are exactly 2.5 apart. Okay, we'll graph it, and then we'll talk about it again, because this is an important idea. All right, so we'll do this. All right, our lowest value is 0, which is kind of nice. So we can do this. Our lowest value is 0. Our highest value is 20. That means our midline must be at 10, because it's got to be halfway between the max and the min. Plus, I can tell there's lots of 10s popping up there. Okay, now one cycle of this graph goes from 2 to 12. So maybe I make my 2, I don't know, about right here. And just kind of coming up with the best scale I can. I say if that's 2, then maybe 12 is about here. The other points are at 4.5, 7, 9.5. Notice halfway between would be 7. And sure enough, we have a point at 7. Halfway between 2 and 7 is 4.5. And sure enough, we have a point at 4.5. Halfway between 7 and 12 is 9.5. And sure enough, we have a point there as well. Our midline's at 10, so let's draw a dashed line there. And we can start plotting these points. 2, 10. 4.5 and 20. 7 and 10. 9.5 and 0. 12, 10. Right, frowny face into a smiley face, and we keep going. And there's our graph. Pretty good answer. The 4 out of 5 answer. What don't I like about it, do you think? No, that's not worth a mark. It's not a bad idea, but that's it. Label your axis X and Y, I think you could say that. Good, that's not it either. Do you notice I have this gap of space here? The graph continues there, right? Like the graph keeps going forever, but it seems like we're leaving this empty space here just because we don't want it. We know what it looks like, or we should. So here's what we're going to do. If I continue this, I'm not just going to put an arrow. Okay? I'd like to show the y-intercept, even if I don't calculate exactly where it is. Do you see that the next point here would be a minimum? Let me just erase this, actually, for zeros in the way. That's 0. The next point here would be a minimum. And the graph would do this. I actually know where that point is. Where would it be? What's its x value? -0.5. The key points are every 2.5 apart from each other, so that continues. So that point's at -0.5. We don't want this empty space here. Okay? So we put it there. Yeah, and then it keeps going. Then we can do the arrows like that. It's a much, much nicer graph. Okay? All right, a couple things I'm going to talk about here with this graph. And I know we've discussed these already, but we're going to do it just one more time. A few things to notice. Notice the amplitude. What is the amplitude here? Nope. Good guess, Emil. 10. The height of the wave is 10. The maximum is 20. The midline, or the axis, is at y equals 10. The period, we already talked about that. The period is also equal to 10. Okay. Look at the equation. Is it shocking that we came up with those values when you look at the equation? Which of these 3 values doesn't shock you when you look at the equation? Anyone? Where's the 12 coming from? Sorry, these 3 values I calculated here. Here, let's do the same thing with the one above. So on the one above, the amplitude was 4. The midline was at y equals 1, and the period was 360. Or 360 degrees. If I look at the equation, is it possible to determine any of those characteristics just by looking at the equation? Yeah, what's one that's easy to tell by looking at the equation? Yeah. The midline's a C value, because the only thing that can change the midline is when you shift up and down. So sure enough, here's our midline. And in this one, here's our midline. Okay, what else? Yeah. Yeah, if you take 360, the standard period, the only thing that can change the period of the graph is if you horizontally stretch or horizontally compress it. That's your K value. So here, our period stayed at 360 because there was no K value. But here, our period went from 360 to 10 because we divided everything by 36. So there you go. And then finally, one other value. I'm going to argue that you can tell the amplitude just by looking at the equation. It's the A value. Because the only thing that changes an amplitude is if you vertically stretch the graph. When you shift the graph up or down, it doesn't change the amplitude. The amplitude is the height of the wave. Okay? But if you vertically stretch it, that changes the amplitude. Hey, A stands for amplitude. Isn't that kind of a nice coincidence too? So, the idea here is that the 5-point method is totally fine. You can always grab a sinusoidal function using that method. I won't stop you from doing that. But we can do a little bit less work if we don't use the 5-point method. And when we go to do this stuff backwards, like tomorrow, given a graph, come up with the equation, it's good to understand this. So when I look at this graph right here, what can I tell right away by looking at this equation? Yes. And midline's 5. Absolutely. What else? Yes, although amplitudes are always positive, so we would just say that it's just 10. What else? Yeah. Very good. Period is 360 divided by 12, and I believe that is 30. Because amplitudes are just the height of waves, so they can't really be negative. So for example, in this case, the amplitude's 10, which just means that this distance is 10, and this distance is 10. It's the distance the max and the min are from the midline of the axis. So it just can't really be a negative value. But we do need to notice that it is negative, which means this thing's been reflected. Okay? So now to graph this, it's actually pretty easy to graph. Okay, we got a midline of 5 and an amplitude of 10. So basically, I'm going to bring this up a little bit. If we have a midline of 5 and an amplitude of 10, that means I can draw my midline here at y equals 5. And I go up 10 from 5, which will put me at 15. That's going to be my maximum. What's my minimum going to have to be? Negative 5, because you're also going to go down 10 to negative 5, which is somewhere here. That's why I put 0 sort of in here somewhere. 0 is not an important point. Okay, so there we go. We also know our period. We also know this is cosine. I'm actually going to start graphing it now. Notice there's no shift right or left, which makes this question a bit easier. This is a cosine curve. We know what a cosine curve looks like on the first page. It does this. But ours is upside down. It's been reflected. So as opposed to starting at its maximum, it's going to start at its minimum, which is down here. Notice I'm not even going to draw a scale yet. I'm going to sketch it first. It's going to go like this. Try to be as symmetric as I can. That was awful, but this is just a sketch. Okay. You could use decimals for a really nice graph. And I got the right curvature, okay? I haven't done any inverted curves or anything like that. The period is 30, which means this whole thing ends at 30. All right, watch this. If this is 30, where is this got to be? 15. Where has, notice this point is the next key point, not the x-intercept. Where's this going to be? This one right here. Not 15, not 0, but 7.5. Right? Halfway between 15. Okay, a little bit trickier, but how about what's halfway between 15 and 30? 22.5. Here's another little trick. Your key points will be every 30 divided by 4, which is 7.5. Remember, 5 key points split a graph into 4 sections. And that's what we have here. We actually have found the 5 key points, but we have not used mapping notation to do that. We just use the amplitude, the period, the fact that it's upside down cosine. There's a beautiful graph. You can draw the little arrows if you want, like this, and like this, but there's a full cycle. I wouldn't use the 5-point method for this one. It's just not that hard. Okay? I prefer this method myself, but you can choose. All right, this is about as tough as it gets. So we got a sine. All right, tell me what you know about this graph. Give me anything. Start with something easy if you want. Yeah. Amplitude's 5, absolutely. What else? Midline is at y equals 10. Yep. Yep. 360 divided by 5, which is 72. Very good. We could also do this little calculation. The key points are 72 divided by 4. Let's see, 72 divided by 4, 36 divided by 18, I believe. So the key points are every 18 apart from each other. This one is going to look like the sine curve. It hasn't been flipped upside down, but there's one other thing that we haven't talked about that happens. Shift right 1. With sinusoidal functions, We actually have a fancier name for that. We call it a phase shift. A phase shift of right one. Why do you think we call it a phase shift? Why not just shift right one? It's the same thing. The answer is because sinusoidal functions are periodic. When you shift them right or left, you're really just changing their starting point, right? Because they keep going forever and they keep repeating. So that's why they call it a phase shift. You're starting the phase somewhere else. In fact, if you shift a curve, if you were to shift this sine curve by 72, you'd actually have the exact same graph because the period is 72. Okay, just something to think about. All right, so we'll see how this one works out. I'll draw my y-axis first. And I like to think about my midline is at 10, so maybe I'll throw a midline in here at 10. If my amplitude is 5, that means I'm going to go up to 15 and down to 5. And now I've kind of decided on what 5 units looks like. So that puts 0 down here. All right, now we have to be careful. We're shifting to the right one. So we have a picture that starts at 1, not at 0. If the period is 72, that means this whole thing takes 73 to finish. Okay? This is a little bit strange. Maybe my 1 should be a little closer to the 0, but I think we're okay. All right, it's a sine curve, so it starts not at its max or min, but at its midline. It's going to start here at 1. It's going to go up, and come back down. It's going to go back down, and it's going to finish there. That's got to be 73 now, so I'll just move my 73 over a little bit. Okay, this doesn't have to be perfect. We're just showing we understand where all the important points are. Okay, now I can start thinking about where all these points are, like this point here, and this point here, and this point here. And I've got a few different ways. I could figure out what this is by knowing it's halfway between 73 and 1. That's one way to do it. Halfway between 73 and 1 would be 74 divided by 2, which I think is 37. Or I could do this. I could look at this and say, hey, this is going to be halfway between 37 and 1. Or I could just add 18 because all the key points are 18 apart. No matter what you do, that's going to be 19. 37 plus 7, this is halfway again. Or I can just add 19, which is, either way, it's 56. No, is that right? 37 and, yeah, 56. Oh, it's 18, I'm sorry, thank you. 55. Ooh. Oh, you really love that. Come up here and teach. All right. Got a good night's sleep, was that it? And you were late today. Oh, wow.
It's a good start.
Very good start. Okay. Here's our graph. It's pretty good. What don't I like about it, though? Yeah. Yeah, this part here, there's like this little, there's just nothing here. There's no reason you would ever leave that kind of important part of the graph blank. So what we could do is we could just back up and say the next key point would be over here at like negative 18, 19 away. And it would represent a minimum. And so the graph would be something like that. Yeah, it's not perfect. I haven't got a perfect scale, but I'm not even using graph paper, so it doesn't matter that much. Not only can we determine where these points are, we determine where all the key points if you keep going more. We just keep adding 19 and keep following the pattern. So, 2 ways to graph sinusoidal function. Yes. Yes. Why do I keep thinking 19 here? Thank you. Negative 17. Any questions about that? Finding the pattern, right? Where would the next point be? If I want, the next point would be over here at the midline, and it would be negative 35. Okay, and then I could keep going if I wanted to, just following that pattern. All right. Regardless of which method you like better, you should be able to determine something like this. When you see a graph, equation, pardon me, you should be able to determine this. What's the amplitude of this first one? 5. Good. The axis, y equals negative 3. the range. That's the possible y values. If this has an axis at y equals -3 and an amplitude of 5, what's the maximum going to be? No, not quite. So you're starting at -3 is your average or your midline. If you go up 5 from -3, what do you have? 2. And if you go down 5 from -3, you're at -8. Okay, when I mean range, I meant like YR. Again, you're right. The range is 10. That's a really good point, though. I meant like this. Y is between 2 and -8. No, you're right. If you wrote the number 10, I couldn't find it. That's also the definition. Phase shift, there is none. Horizontal expansion or compression and the factor, it's a stretch. Expansion or you should call it stretch, but whatever. Expansion by 2. Because we're going to multiply our x size by 2. What's that make the period in this example? 720. Yeah. Why don't you try these next two and see if you can get them? All right, so for the next one, amplitude's 10. Your axis is at y equals 5. Okay, so y equals 5 is your axis or your midline. They mean the same thing. I always call it the equation of the axis, and I've heard people start calling it the midline. And so actually, that's a really good name for it. If you go up 10 from the midline, you get 15. You go down 10, you're at -5. So the y values are between -5 and 15. The phase shift is to the right 30. This one has been an expansion. Actually, it's a compression, technically. You would divide by 2/3, which is the same as timesing by 3/2. Okay? It's also a reflection of the y-axis, which we don't usually do, but there it is. The period would be 360 divided by 2/3, which is the same as 360 times 3/2. Which is, let's see, 180 times 3, I think 540, is that right? 540? What's fine? Is that good? All right, what do you have to be careful of with the next one? The amplitude's 15, by the way, not -15. The midline is at y equals -3, which means we go up 15 from -3 and down 15. So down 15 would be -18. Up 15 would be 12. But before we do the rest, you gotta be careful with this one. Gotta factor. It's not in the right form. You gotta factor out the 3, and you actually get x plus 30 when you do that. So we get everything right but our phase shift if we didn't realize that. The phase shift is to the left 30. This one is the compression by 3, or compression by 1/3. You divide by 3, or this one should have been expansion, by the way, not compression. Sorry, expansion. That's super important, but there we go. And then 360 divided by 3 is your new period, so it's 120. There you have it.